In this video I'm going to demonstrate how to calculate the resistance of a piece of material based on its dimensions and the resistivity of the material it's made from. So here I have a rectangular solid piece of material, and the formula for this for the resistance of this material is going to be equal to the resistance is equal to some natural resistivity of the material times the length of the material. And in this case, let's just say the current is coming in one end and then coming out the other end. Okay, and so you might imagine that the longer this is, the higher the resistance will be, and so that multiplies directly. And so this is, I'm going to take this as the length, okay, and then this is if you think about the cross-sectional area of this device, and in this case it's rectangular, but it could be circular or some other shape. If you had a wire, you might expect a circular cross-section, but in this case it's a rectangle. The more cross-sectional area you have, the less current crowding you have, and the lower the resistance is. So this is related inversely to the cross-sectional area. And since this is a rectangle, I'm going to break this down a little further. I'm going to look at the thickness of this film. So I'm going to rewrite this as bulk resistivity. And I know that area is going to be thickness times the width of this feature. Okay, so that's thickness times width. And then I want to look at an example here, and so let's just say a common feature size for an electronic device these days is maybe 90 nanometers. Typical thickness might be 7,000 angstroms, and let's just say that the length of this feature is 10 micrometers long. Okay, let's also assume this is made out of aluminum, and I can look up on a website and determine the bulk resistivity of aluminum is 2.65 times 10 to the minus 8th ohm meters. Sometimes the bulk resistivity is given in ohm centimeters. In this case it was given in ohm meters, and so when we do our conversions, I'll convert everything to meters so that the units cancel out properly. Okay, so let's take a look at that. So again, starting with my resistance equation, it's equal to bulk resistivity times length divided by thickness, and also divided by the width. Okay, and so plugging in bulk resistivity of 2.65 times 10 to the minus 8 ohm meters, and the length of 10 micrometers, and dividing by a thickness of 7,000 angstroms, and dividing by a width of 90 nanometers. Okay, now these units are this is in meters, this is in micrometers, nanometers, and angstrom. An angstrom is, if you remember, 1 angstrom equals 10 to the minus 10 meters. Okay, and so the easiest way to do the unit conversion for this type of calculation is to replace the metric prefix or the term angstrom with its equivalent. So since a micrometer is 10 to the minus 6 meters, a micrometer is 10 to the minus 6 meters, a nanometer is 10 to the minus 9 meters, and an angstrom is 10 to the minus 10 meters. In place of this, I'm going to write the metric. I'm going to replace those metric prefixes with the power of 10 equivalent of that. So let's look at how that comes out. So now I still have 2.65 times 10 to the minus 8 ohm meters, and multiplying by 10 times 10 to the minus 6 meters. I'm dividing that by 7,000 times 10 to the minus 10 meters, and I'm also dividing by 90 times 10 to the minus 9 meters. Now I say dividing, even though I'm writing times here, when I use the calculator to figure this out, I'm going to take this number times this number divided by this number and divided by this number. So I multiply by all of the numbers in the numerator, but I have to divide by all of the numbers in the denominator. I'm also going to use my scientific notation feature on the calculator to quickly enter these powers of 10, and that'll make it go a little easier. Alright, so I'm bringing in the calculator, and you can follow along on how I enter these into the calculator. So the first one is 2.65, and the power of 10 is e to the minus 8th times 10 e minus 6. I didn't have to type in times 10 or anything. I just hit the EE button, and it has that times 10 built into it. Then I'm dividing by 7,000 EE minus 10, and I'm also dividing by 90 e to the minus 9. Okay, and then I hit enter, and that gives me a resistance of 4.21. I have 3 sig figs in some of these. I'll just use 3 significant figures for this, so it's 4.21 ohms. So if I look at the units here, the meters cancel here and here, and I'm just left with the units of ohms, so 4.21 ohms. Now before I leave this example, I want to do one other calculation, and that is something called sheet resistance. And so there's another property of a material that's commonly calculated. It's called sheet resistance. And sheet resistance is equal to the bulk resistivity divided by the thickness. And we can think of the units for sheet resistance are ohms per square. And one way to think about sheet resistance would be that's how much a square piece of the material, what the resistance would be of a square piece of the material, okay, if the length was equal to the width. Okay, so if we set the length equal to the width, and if we had our previous formula where we have length over width, these two are equal to each other, you'll see that they cancel out. So these two cancel, And we're just left with, in this special case where the length is equal to the width, rho over the bulk resistivity over the thickness. And we call that special parameter sheet resistance, and it's actually quite easy to measure that. There's some tools in the laboratory that can measure sheet resistance quite easily. So I can calculate that for this example, 2.65 times 10 to the minus 8th ohm meters divided by 7,000 times 10 to the minus 10 meters. And when I do this calculation, I'm going to see the meters units are going to cancel, and so let's do that. So it's 2.65 times 10 to the minus 8 divided by 7,000 times 10 to the minus 10. And so that comes out to be equal to 0.0379 ohms per square. So the units for sheet resistivity are typically ohms per square. Now there's two other things that you can do with this. One of them would be, since it's quite easy to measure sheet resistivity in the lab, you can rearrange the formula for that to obtain the thickness. So if I look at the formula for sheet resistance, it's equal to the bulk resistivity divided by the thickness. Now, it's actually usually easy to obtain this value, so often this is used to calculate the thickness of a film. So I need to rearrange this formula a little bit. I'm going to multiply both sides by the thickness, and that results in, and I'm going to divide both sides by the sheet resistance, and that gives me a new formula. The thickness of the film is equal to the bulk resistivity divided by the sheet resistance. And we can use that. That's often used to calculate the film thickness for a conductive film.